All right, guys, so today we are going to look at medians and altitudes, which are going to give us a lot of different information about triangles. So, the median of a triangle is a segment whose endpoints are a vertex and the midpoint. So, if we look at this, if we take any vertex of a triangle, and the midpoint of that side opposite. There we go. So the vertex, excuse me guys. So a vertex and the midpoint of the opposite side, we call this the median. So I could use this vertex and the midpoint of this side, this vertex and the midpoint of this side. So there's a lot of vocabulary in this section. So you'll be wanting to make sure you kind of keep track of it because that's a lot of what's going to be referenced here. Now, when we talk about the medians, the concurrency, so that's like the intersection. The concurrency of the medians, the three medians of the triangle meet at a point. So if I draw all three of these medians, what they're going to do, you'll have a triangle that looks like this. So this has three medians, and they're going to meet at a point, and we call that point the centroid. So the centroid is where these three medians meet. So if I draw in all three medians in a triangle, so from the vertex to the midpoint of the opposite side, that's going to give me my centroid. And when we look at that point of concurrency, that point where they intersect, so right here, that's my centroid. So my centroid has some properties. So if I look here, it says DC is 2/3 of DJ. So if I look at this whole median, D to C is going to be 2/3 of the distance of the whole thing. So this piece is essentially 2/3, this piece is 1/3. EC, if I look at E to C, so from the vertex to the centroid, that's always going to be my longer piece. That's 2/3 of the total of E to G. So again, this piece is 2/3, this piece is 1/3. And then the same thing with F to C. From that vertex to the centroid, that piece is the 2/3. C to H is the 1/3 of that total distance. So I can use these relationships here to set up a formula and solve, or set up an equation and solve. So let's look at this example. So it says if x to a is 8. So I'm going to kind of just redraw because I'm just looking at, so we'll say my centroid's right about here. So there's x, there's a, there's b. So I'm taking this line here, and I'm just going to kind of redraw it to give myself a little bit more space. So they said x to a is 8. So from here to here is 8. I want to find out what x to b is. So if I know xa equals 8, I know that piece of information. I know that x to a, because that's that endpoint to the centroid, this is going to be 2/3 of my total distance. This is going to be 1/3 of my total segment length. So I can say, well, XA is equal to 2/3 of that total length, XB. So I'm just basically grabbing those formulas from the box above there and filling in. Well, I know x to a is 8 equals 2/3 of my total length, so we're going to call it my total length x. I know that's xb, so that's the total piece. So actually, when I look back up here really quick, I'm not going to call that x. I'm going to say this total distance from x to b is x. So when I have a fraction, the easiest thing to do, 2/3 times x, instead of dividing both sides by 2/3, I'm going to multiply by the reciprocal. So if I multiply by 3/2, 2/3 and 3/2, those are reciprocals. That's going to multiply to 1, so that's going to be taken care of. And then you can either plug 3/2 into your calculator. I can do 3 times 8 is 24. 24 divided by 2 is 12. So I just did the 3/2 times 8. So then that gives me that total length is 12. And they did say what is x to b, so I can say that's 12. They didn't ask me here, but I could figure out this piece. Well, 8 plus what gives me 12, so a to b would be 4. So then I can fill in kind of all that missing information that I might need for one of these problems. So, all right, so now what we're going to look at is the altitude. And the altitude is essentially the height of any triangle. So like when I look at this triangle here, if I look from point P, my height is actually this perpendicular distance. So when you don't have a right triangle, the altitude is what you use to find your height. So this is the perpendicular segment from a vertex of the triangle to a line on the opposite side. Now that line is not always going to be inside the triangle. So to a line containing the opposite side. So this can be outside of the triangle. So for example, when I look here, this height, this is the height or the altitude of my triangle. PR is what I would call the altitude. I have to extend this bottom side to be able to actually find this height of this triangle. So the highest point to the base here. So the line that contains the altitudes of a triangle are concurrent. So again, these lines meet. If I draw my 3 altitudes, so here, different triangles are going to look a little bit different. So if I draw from a vertex to the opposite side at 90 degrees, vertex to the opposite side at 90 degrees, vertex to the opposite side at 90 degrees. So when I have an acute triangle, it's going to look something like this. And that is my point of concurrency. We call the point of concurrency of the altitudes, this is the orthocenter. So when I do the same thing with a right triangle, so here, there's one altitude, there's 90 degrees. There's one altitude because it's from the vertex to the opposite side at 90 degrees because that's the right triangle. And then the last one's from that vertex to the 90 degrees. So here, my orthocenter is actually, I'm doing a really bad job of that. I'm going to do it a little better. My orthocenter is actually this vertex. So it can meet at a corner in a right triangle. And then when we're looking at an obtuse triangle, this one's a little bit different. So from the vertex to an opposite side, this one, there's my 90 degrees, but you extend this line because for the other two sides, from a vertex to the opposite side, that's where it meets it. And again, I have to extend it. Vertex to the opposite side, there's where the 90 degrees, there's my altitude or my height. There's an altitude or height. There's an altitude or height. But these ones meet outside of the triangle. So in an obtuse triangle, your orthocenter is going to be outside of the triangle. So different ones are going to look a little bit different. So we have all this vocabulary here that we're going to be talking about, and we're going to get a much closer look at this when you look at your classwork. So the ones that we talked about already here, when I talk about my perpendicular bisectors, oh, just kidding, we didn't talk about this one yet. So if I take any side and take a perpendicular bisector, so 90 degrees through the middle, through the midpoint, perpendicular bisectors. So this is called a circumcenter. We'll talk about those a little bit more in class. The angle bisectors, if I cut every angle in half, then that's where they meet, and that's called our incenter. And then the two we've talked about is the median. So the median is a vertex to the midpoint of the opposite side. Different than a perpendicular bisector because that's through the midpoint of the other side. That is a bisector, but these ones have to be at 90 degrees so they look different. Median is vertex to the midpoint, not perpendicular. So those meet at the centroid, and then the altitudes are essentially the 3 heights of a triangle are meeting at the orthocenter. So we'll take some time together and work through the classwork and the lesson quizzes of this section, and we'll spend some extra time reviewing this one this week. It's a lot of vocab and being able to identify what a perpendicular bisector is, an angle bisector, a median, and an altitude. That's a lot of what we'll do in this section. All right, guys, have a great night.